Hello, this is a picture of a lemon tree which contains alkenes in its oils. I'm going to the next slide. Here it is. As is my custom, to give you something to think about. God's incommunicable attributes are his self-existence, unchanging nature, and infinities, or those attributes present in infinite measure. Taken together, these cement the notion of uniformity so central to the scientific enterprise. That is, scientists assume that the universe is everywhere, governed by the same underlying principles, rendering it capable of being studied. And that's what we do in science. Okay, today we're going to talk about alkenes in Chapter 3. Chapters 1 and 2 have prepared us for looking at organic reactions. We saw in Chapter 1 a review of general chemistry principles, and in Chapter 2 we looked at 5 classes of organic compounds, that is, the products of organic reactions. Chapter 3 looks at the structure and nomenclature of alkenes, hydrocarbons that contain carbon-carbon double bonds. You will learn about how electrons move during the course of a reaction as new covalent bonds are formed and existing covalent bonds are broken. We'll use curved arrows you'll see in the diagrams. We will also look at the principles of thermodynamics and kinetics, principles that allow us to understand how and why organic reactions take place. Future chapters down the road, later in the semester, Chapter 4, Reactions of Alkenes, Chapter 5, Stereochemistry, or the arrangement of atoms in space, Chapter 6, Reactions of Alkynes, Chapter 7, Electron delocalization and resonance, and Chapter 8, Substitution reactions of alkyl halides, and Chapter 9, Elimination reactions of alkyl halides, and then on to Chapter 10, reactions of a combination of different compounds, alcohols, amines, ethers, epoxides. And then Chapter 11 is organometallic compounds. Chapter 12 will be radicals and reactions of alkanes. And then finally, Chapter 13, mass spectrometry, infrared spectroscopy, and UV visible light spectroscopy will conclude the semester. So here we go with ethenes. Alkenes. This is a photograph of ripening tomatoes. Ethene is a plant hormone that causes tomatoes to ripen. Of course, ethene is the smallest alkene, and it's a 2-carbon compound with a double bond between the 2 carbons. Here are some other alkenes that are important in plants and insects. Hydrocarbons that have a carbon-carbon double bond, of course, are called alkenes. Smallest of the alkenes are ethene, as I've described, a carbon-carbon double bond, 2-carbon compound. Also known as ethylene, E-T-H-Y-L-E-N-E is its common name, ethylene, which you need to remember. Of course, ethene, E-T-H-E-N-E, is the systematic name. Alkenes were first known as olefins, O-L-E-F-I-N-S, or oil-forming compounds. Many of the flavors, hormones, and insect pheromones belong to the alkene family. Here are 2 more examples. Muscular and farnesene. And back to the previous slide again, didn't mention, but these are 3 examples of alkenes in plants and insects. Why are they alkenes? Because they have double bonds. You can see double bonds in all of them. There's one, there's a double bond, and the 2 double bonds in these various compounds. Limonene and beta-phelantrine and multifidine. And you can see how they're found in nature. And here's 2 other examples, muscular and farnesene. Muscular is a pheromone in houseflies, and farnesene is found in the waxy coating on apple skins. Long chain hydrocarbons, but they each have a double bond, or in this case, more than 1 double bond. Muscular is a long chain carbon chain that contains, as I said, one double bond, and farnesene has branching on the carbon chain that contains 4 double bonds, as you can see there. Okay, let's go on here. Molecular formula and degree of unsaturation. The degree of unsaturation is the presence of multiple bonds. For example, double bonds in alkenes. We're talking about non-cyclic compounds that are also acyclic. The general formula for a hydrocarbon is, and you can see there, CnH2n plus 2, minus 2 hydrocarbons for every pi bond, as in a double or triple bond, and or ring in the molecule. So the general formula for alkanes is also CnH2n plus 2. So let's look at this a little closer. Here is the next slide for alkane and alkene. And there are differences between alkanes and alkenes, as you can see. The characteristic formulas are given. For an alkane, CnH2n plus 2. So this is a 4-carbon, 5-carbon alkane. So it's going to have 5 carbons, and it's going to have 2n plus 2, or 2 times 5 plus 2, number of hydrogens, which would be 12. 3, 5, 7, 9, plus 3 is 12. An alkene has the general formula, a characteristic formula of CnH2n because it has one double bond. If we take the 2n plus 2 of this formula here and subtract 2 to account for the double bond, it would be 2n plus 2 minus 2, which is 2n. Also, with a cyclic alkane, the formula is CnH2n, where we have accounted for the presence of one cyclic ring in the compound. So 2n plus 2 minus 2 gives us this formula. With a cyclic alkene, we have a double bond and a cyclic component in the compound. So we would subtract minus 4, 2 for the double bond and 2 for the cyclic component for the ring. So 2n plus 2 minus 2 minus 2 is 2n minus 2. So you can see where the formulas come from. This concludes part 1 of our discussion in alkenes.